Okay, so I am Enrique Bello, and I recently finished the PhD thesis. It's recently made public, so if you have interest, you can take a look maybe. The thesis is called Analysis of Turbulent Transport in Hall Effect Plasma Thrusters. Okay, and this is the contents that I'm going to be following today. As my colleagues mentioned the other day, in the context of space propulsion with plasma, we have two big technologies, which are the gridded ion thruster and the Hall effect thruster. Okay, they are mature; they have been flying for many years, but they are not perfectly well understood. Okay, we have very complex plasma physics phenomena taking place here. So this prevent us from having, for example, predictive numerical codes, which would be really important. Okay, so very fast, I'm going to, well, my thesis focus on Hall effect thrusters, and really fast I'm going to explain how they work, okay? These devices, conventional devices, have this kind of annular shape with an anode and a cathode that are electrically connected with a voltage source. We have a cathode that is also an electron gun, okay? Electrons are injected here. We have a neutral gas injected through the anode. Electrons and neutrals collide and the neutrals get ionized. And these ions are accelerated downwards, and this is what provides the thrust. Okay, this is all possible because the electron population is confined with an magnetic field that is almost radial. Okay, and this increases the residence time of the electrons. Okay, so in a very simplistic view, we can decompose the electron motion in the different contributions. Okay, we have the gyro motion around the magnetic lines, which is what provides the confinement. We have motion along the magnetic lines, which is almost free. We have a drift in the E cross B direction of the electrons, and then we have an axial drift, okay, in the direction of the electric field, which in principle is due to collisions. However, when the axial transport of electrons is measured, is very high if we consider only collisions, okay? So there must be other phenomena involved that is enhancing the transport of electrons. The main candidate is the presence of azimuthal oscillations and turbulence induced by plasma instabilities. Okay, and this is the field in which my thesis tries to contribute. Okay, so my thesis is expected to give an answer, or to contribute to give an answer to several questions. For example, what are the main stability modes triggering the turbulence? And before talking about the stability, we have to talk about equilibrium. Okay, so one first step is to find equilibrium solutions of the Hall thruster discharge with a certain model, and then we can study the linear stability of those equilibrium solutions using different approaches. For example, you can use a global stability approach with a fluid model, a local stability approach using fluid models or kinetic models. There are several ways, okay? But at the end, these kind of linear stability approaches are not enough, because turbulence and oscillations of big amplitude are very nonlinear, okay? And at the end, you have to go to nonlinear simulations, okay? And in the case of my thesis, we have developed a two-dimensional particle-in-cell code to do these kind of simulations. And in the thesis, I have some simulations of simplified scenarios that at the end we expect to use that information from those simplified scenarios to understand the effect of instabilities in our type of plasmas, and how and probably these simplified simulations would help us to explain more complex simulations in the future. Okay, so from the point of view of fluid modeling, okay, I will start with the equilibrium. Okay, we have a certain set of fluid equations for electrons, neutrals, and ions. And in the equilibrium, we assume that the solutions are stationary, and we have only variation along the thruster axis. And okay, we obtain certain equations, a one-dimensional model. We can solve it, and this is the kind of solutions that we expect to obtain from this model. Okay, we obtain the axial evolution of several plasma magnitude, electric potential, velocities, densities, temperatures. Okay, compared with other models in the literature, the model shown in the thesis has some novelties and some new findings. For example, we include the effect of the electron azimuthal inertia, which happens to be important in some regions. We assess the importance of gyroviscous terms, corrections to the pressure tensor. We have a model, a new model for the cathode that is volumetric instead of being infinitely thin layer. And we have also the study of several Plum conditions and how they affect the inner part of the solution, the outer part, etc. All these findings are summarized in a journal paper. And at the end, these equilibrium solutions, as I mentioned, can be used to study the stability. Okay, in the thesis, we include a global stability analysis. In this kind of analysis, we take also our fluid equation that I was mentioning, and we assume that every plasma variable is the addition of an equilibrium part, okay, the part that I was talking before, and a small perturbation. Okay, you linearize the equations. We assume that the perturbations have this shape, okay? We have a complex amplitude that depends on the axial coordinate, and in the azimuthal and time coordinates, the variation is sinusoid. And at the end, mathematically, we have to solve this kind of problem, okay? This is a system of linear, homogeneous, ordinary differential equations, and for each given azimuthal wave number, we obtain the complex frequency of the waves and also the modal shapes, okay? This kind of analysis, we focus on high frequencies. For that reason, we only consider ion and electrons, and is able to solve the axial inhomogeneity of the plasma consistently, which is not possible with local analysis. Also, compared with the existing literature, our model fully takes into account the pressure and electron inertial effects, okay? Okay, and the type of results that we obtain. Okay, as I mentioned, we can obtain frequency and growth rate of the different waves, the different modes in the plasma as a function of the azimuthal wave number, okay? And in terms of the growth rate, we obtain two main modes, okay? We have these modes here, which are near Plum instability modes. These are modes of frequencies of the order of the megahertz. They involve mainly ions. They are very robust to parametric changes, and they seem to be related with the regions of negative magnetic gradient, okay? And then we have these other modes here, which are subdominant, and they are near anode instabilities. They happen mainly close to the anode. They have lower frequencies. They involve ions and electrons, and they are very sensitive to parametric changes, for example. Okay, so now let's move to kinetic simulations, nonlinear simulations, and as part of the thesis, and also as part of the thesis of Alberto Marin Cebrián, we have developed a two-dimensional particle in cell code, which we recently baptized as Picasso. I'm not going to enter into the details of these kind of codes, but at the end, you have to know that what we want is to solve directly the velocity distribution function of the species in our plasma by solving the Boltzmann equation. But instead of solving directly the Boltzmann equation, we discretize the distribution function in macroparticles, and we solve the motion of those macroparticles instead, okay? As an additional models, we need the Poisson solver that gives us the electric field and module for collisional operations. Okay, this code had been subjected to a deep optimization process during my stay in Laplace laboratory in Toulouse. We have completely changed the parallelization of the code to work only on private variables and avoid complex algorithms. We have tried sorting algorithms to have a better usage of the cache memory of the CPU. I have tried the Intel compiler, which gives a lot of computational savings with respect to the EGNU compiler, at least for our workstations, and also different types of solver for the Poisson, okay? At the end, during my stay, if I compare computational times before and after, I obtain an increase in computational performance of 90%, okay, which I think is quite good. Also, an important part of the stay was the participation in an international benchmark, okay, in which we have been comparing solutions obtained with our codes with those obtained with many other groups, okay, for a certain particular simulation, okay, that I'm not going to explain, but at the end, the bottom line is that we compare several profiles for several plasma magnitudes. Our results are the broken line here, and we are well positioned compared with other groups, and in general, our solution agrees with most of the groups that participated in the benchmark. Okay, and finally, the last part of the thesis is using the code to simulate instabilities that are relevant in the context of Hall discharges. From the point of view of the theory, for the characteristic of our plasmas, the local kinetic theory predicts the electron-cyclotron drift instability. And in the thesis, I have some very fundamental simulations that try to be very, very close to the theory, okay? If we simulate in a periodic domain, which is essentially the theoretical case, we observe the growth of an instability, the saturation, but at the end, in the long term, we don't achieve a significant amount of electron transport or oscillations. So this is not very interesting for us because in real discharge, we would expect to have long-term transport, okay? However, when we change periodic conditions and instead we inject and remove particles through axial boundaries, we obtain different regimes depending on the velocity of the ions, okay? Depending on how the ion residence time compared with the saturation time of the instability, okay? So what you can see here is the final picture for 3 different simulations with different ion velocities. I'm representing the space evolution of the azimuthal electric field, and you see that for slow and fast ions, I don't get a significant amount of oscillations, but there is an intermediate regime in which I achieved significant oscillations and also significant amount of transport, okay? So I'm not going to make any conclusions because basically my presentation was conclusions of my thesis. So to finish, just a list of achievements. In the thesis, I include 2 published journal papers and 1 that is submitted. I have participated in other 4 journal articles and have around 10 contributions to conferences and workshops. Okay, so that's all. If you have any questions, I'm glad to answer.